we're going to be able to see when something has or is modeling exponential growth is whenever our rate of growth or derivative is directly proportional to the quantity at a specific time. If we look at this first example, let's figure out what all we know. Okay. Well, first and foremost, since it's exponential growth, we're going to have some equation that looks like y equals c times e to the kt. All right, but we're going to go ahead and define these in different ways, right? So instead of y, we're going to say p, and p is going to stand for population. So we're dealing with bacteria. Instead of c, which was our initial condition, we're going to say initial population, or p naught. And then e, and we're going to keep saying k times t, where k is a growth constant. It's going to stay the same. And t is time. In this case, it's hours. All right, so what are these do we already know? Well, we know that our initial population was 20,000. We know that after 5 hours, our final population was 400,000. And so we can use those three pieces of information to go ahead and find this last part, or the growth constant. That's what it's asking. It's asking for the equation. The main piece of the equation that we don't have, is that k, or that growth constant. So let's write this out. We have 400,000, is equal to 20,000 times e to the k times 5. All right, we're going to go ahead and get this exponential piece by itself. We want to get that by itself before we do anything else. So we're going to do that by dividing by 20,000. So we get 20 equals e to the k times 5. All right, now we want to undo this e to the x piece. We don't want that anymore. We want to get rid of e to the k times 5. Not e to the x, e to the k. To undo that, we're going to take the natural log of both sides. The reason why we want to take the natural log of both sides is, well, the natural log of 20, that's going to be a number. All right, and the natural log of e to the k times 5. If you remember, natural log and e to the x, or e to the k in this case, undo each other. So this whole thing is actually just k times 5. All right, so we can finish this off just by dividing by 5. Getting k is equal to the natural log of 20 divided by 5. But because we're dealing with a real-world situation, we actually want to plug that into our calculator, and we get an approximation of 0.599. Okay? And what we can do with that is we can go ahead and write our final equation now. For any population, for any time, our population is going to be 20,000, because that's where we started, times e to the 0.599 times t. And that's a t equals 10, we'd plug 10 in and get a new one. T equals 500, we'd plug 500 and get a new one. All right, and this is one of those instances, if you remember from when we first talked about exponential growth, this actually probably wouldn't work. This would be more of a logistic growth, because at a certain point, you have a maximum population that you can reach. Let's try this next question, which is going to be a pretty similar setup. We're going to use the same type of equation. Don't worry, my son is perfectly fine. All right, but with this equation, we don't have as much information. All right, all we know is that it doubles. We don't know what the initial population is. We don't know what the final population. But because we know that it doubles, it really doesn't matter, because we can just say, well, let's make our initial population 1. And I know that, well, if it doubles, my final population is going to be 2 when t is equal to whatever our growth time was, which was 9. So using this information, we can set up that 2 is equal to 1 times e to the k times 9. All right, and we can use that to solve, right? We're going to solve in the exact same way. We're going to divide by 1. Well, we don't really need to. So we can just go ahead and take the natural log of both sides. So the natural log of 2 is equal to the natural log of e to the k times 9. Well, this side is exactly the same situation that we've gotten so far. It's always going to be that situation. All right, we're going to get the natural log of 2. Let me write that in there. Natural log of 2 is equal to just k times 9, right? That undoes each other. Okay, continuing this on, we get that k is equal to the natural log of 2 divided by 9, which tells me that k is approximately 0.077. Okay? And what we're going to do is continue this discussion, say, well, let's say we actually know what our initial population. Let's say this fruit fly colony, which I really didn't set up the equation, but let's say the fruit fly colony actually starts at 100 fruit flies. We know that now. Now that we know that, we can set up our actual equation. P of t is equal to 100 times e to the 0.077 t. All right, and so this next question says, well, how large will it be, or what's the population going to be? What's p when t is equal to 41 days? All right, and this one actually has no calculus in it whatsoever. All we're going to do is take 100 times e to the 0.077 times 41. All right, we type this all in, we do all of our calculator work. There's really not much to it. I would suggest, if you're typing your calculator, get a number for this piece first, and then take that number and multiply it by 100. All right, but what we're going to get here is we have an approximation of, because we're rounding to the nearest fruit fly, 2350 flies. Okay? All right, then continue on. Let's actually do some calculus. Sorry. The next question says, well, how fast will the colony be growing at 41 days? When I say how fast, I'm asking for our favorite piece of this class, the derivative. Okay, growth rate, speed, anything like that is going to be derivative. So this is really asking, well, what is... And this is, again, at 41 days. So it's asking, what's p prime of t, or what's p prime of 41? Okay? Well, first thing, let's find the derivative. P prime of t is going to be, because we have our nice, let's go back up here, looking at this, all right, our nice equation. When we're dealing with an exponential, actually we're dealing with this equation up here. This one has the 41 plugged in. We're dealing with an exponential. It's actually pretty easy to take our derivative because we can just multiply our exponent out in front, that constant, right? This is just going to be 0.077 times our original function, 100 times e to 0.077 times t. Okay, and really you can just multiply that constant out in front. And what's nice about that is we can actually see in a pretty easy way that we're just really going to multiply this 0.077 by our original flies, right? We can just multiply this out. We're going to plug in p prime of 41. We're going to get, this is equal to 0.077 times 100 e to the 0.077, you're going to write that a bunch, times 41, which is approximately, when you do all your calculator work, 181, and this is 181 flies per day. All right, so each day we're getting a new additional 181 flies. And why we had to know at a certain day, why we had to know that it was at day 41, is because we had more flies at day 41, so we're going to be getting more flies, right? That's how population works. You have more people to make more people, you're going to have more people. All right, and then this last question, we're running out of time here. I only got about 30 seconds before my video ends. I'm not going to do this for you, but I'll show you how to set it up. All you're going to do is say, well, I want to know when p equals 800, right? When the population equals 800, what was t, right? So I'm going to take 800 equal to 100 times e to the 0.077 t and solve that.